All right, so our class for this evening is on work, power, and efficiency. We'll start with the definition. Work done by a force is the product of the force and the displacement of the object. So let's write that relationship here. Select the pen tool. There we go. Work equals force times displacement. Now, when work is done, there's an energy change. So this is also equal to the change in energy. Okay, so that's our first work equation. We'll put a box around that one. Now, because work is a force times a displacement, the units of work must be newtons times meters, which is defined as a joule. Now, let's look at a couple of examples. Okay, when you push on something, the energy change that takes place is chemical energy in your muscles gets converted to motion energy in the object. And motion energy is referred to as kinetic energy, Ke. Friction force takes motion energy, which is kinetic, and converts it to thermal energy, when we use the symbol Q for thermal energy. Gravity, well, that takes motion energy, kinetic energy, and converts it to height energy, which is potential. And actually, that transformation works both ways. Gravity, if you start with a high object high off the ground and drop it, then its height energy gets converted to motion energy on the way down. Okay, next, power we define as the rate of doing work, how quickly we do it. So the power is the ratio of work over time. Now, work is in joule units, time is in second units, so a power unit must be a joule per second. That's a J there per S, joule per second. And that's got to be, or rather that is defined as a watt. So watt is the unit of power and it's a joule per second. Now we can do a little derivation there. Put a box around that one first. I don't know why it's not completing that box, but you can do so. We could do a little derivation. If power is work over time and work is force times displacement, we see here that we have displacement over time, which is, of course, an average velocity. So we can state then that a power, in addition to being a work over a time, is also a force times an average velocity. And once again, we'll put a box around that one, just like that. And that's supposed to be V, oh, there it comes, average velocity. So power is the product of force and average velocity. All right, let's try an example then. Okay, actually before the example we have one more definition. Efficiency, it's the ratio of the output energy or power to the input energy or power. For instance, we put a certain amount of food energy into our bodies and we get out useful work. We put a certain amount of gasoline energy into our cars and we get out a certain amount of useful work. The efficiency is the ratio of those two, and it's usually expressed as a percentage. The Greek letter eta is used for efficiency, and an eta is kind of like an N with a long tail. But it's actually an I in Greek, so it's got an I sound to it. All right, so that's our final definition for this first lesson in our new unit. Let's try an example. So we have a 250 kilogram mass. We're lifting it at a constant speed up 12.5 meters. Find the work done, power required, and then the efficiency of the motor. We'll do that over here on the ink pad. So first we'll draw a force diagram. So we're lifting this mass at a constant speed. Clearly there'll be a downwards force of gravity, which is mg. And then there's going to be an upwards lifting force. Now, because the speed is constant, this tells us, of course, that the acceleration will be 0, which implies in turn that the forces are balanced. So that tells us that the applied force just equals the weight mg. So for 250 kilograms, we can multiply by 9.8, and then we can determine the amount of force that's required. That's 2450 newtons. Okay, now we want the work. So part A says find the work. Of course, work has been defined as the product of force and displacement. Now, we know the distance is 12.5 meters, and now we know the force is 2450 newtons. So we simply take the product of those two. Now we end up with Newton meters, which is joules for the units, and then we end up with 2450 times 12.5 is 30,625. That's the amount of work that's done. The next thing that we're asked for is that we required power. Now, power is work over time. We know the work, but we don't know the time. But power is also the product of force and average velocity. And we've got 2450 newtons of force, and we're told the velocity is, the crane is lifting at 2 meters per second. And consequently, the product of those two, that's going to be 4,900, and then this is Newton meters per second, which is joules per second, which is a watt. Next, find the efficiency. Well, the efficiency is a ratio of output power to input power, or output energy to input energy. Now, the input power in this case is going to be the electrical energy that goes to the motor. The output power is going to be the mechanical power of the moving object. Now, the output power we just worked out is 4,900 watts. And we're told in the question that the motor is consuming or using 10 kilowatts or 10,000 watts of electrical energy, 10,000 joules each second. So canceling off a couple of zeros, you get 49 over 100, which is 0.49, which is 49% efficient. Okay, so that's example 2. Next, direction. Well, work is a scalar quantity. It doesn't have any direction, but it can be positive or negative. And a force that's in the direction of the motion is going to speed the object up, and that's going to do positive work. Okay? So we say that positive work is done when a force is in the direction of motion. Okay, so a force in the direction of motion does positive work. We'll highlight that. And a force that's opposite to the motion, this might be a frictional force, that does negative work. And because that causes the system to actually lose energy, and as a result, the energy change is negative. Okay, so let's go back. We'll just highlight these one more time. 1, 2. Hopefully this will stay with us this time. There we go. All right, so here's another example. So we're taking a 10 kilogram mass and pulling it across a roughed floor. So we'll start once again with the force diagram. So here's the mass, here's the surface. We're pulling it with a force of 50 newtons, so we'll call that force F. And clearly there will also be the weight of the object, mg, the normal force from the floor, Fn, and then the frictional force, resisting sliding. Now, in the y direction, the forces are balanced. So the normal force equals the same as the weight. But of course, we know that friction is mu times the normal force. This friction depends on two things, on the surface condition and the squeezing force. So the mu constant is given as 0.1, and the normal force will be the same as the weight, so 10 times 9.8 is 98 newtons. So we see that we actually have 9.8 newtons of friction. So we're now ready to find these works. So first of all, the work of the pull. Well, we know work is a force times the displacement. So we're pulling with 50 newtons. How far is it going? We're told that it's 3 meters. So we have 150 newton meters, or 150 joules. Now that is the work done by the pulling force. That's related to the chemical energy that the person used. Next, let's find the work done by friction. And this is going to be related to the thermal energy created in the floor. Well, work is a force times the distance, but because friction is opposite to motion, this is negative, and we're going to have to manually insert that negative sign there. So we've got negative 9.8 newtons of friction acting over a 3-meter distance. That's negative 29.4 joules. Now that represents mechanical energy that gets converted to thermal energy and is lost to the system. So when we find the total work done, well, the system gained 150 joules of mechanical energy because you were pulling on it, and then it lost 29.4 joules due to friction. So we have 120.6 joules of net mechanical energy. So what's the efficiency of this process? Remember, efficiency is the N with a tail on, the Greek letter eta. Well, that's the useful output over the input. The useful output is this 120.6 joules of mechanical moving around energy. The input, of course, is the 150 joules that were committed to this process. So what is that? It's 120.6 divided by 150. That is 0.804, or in terms of a percentage, that's 80.4% efficient. Okay, moving right along. Let's now consider the work done in 2D situations. So, for instance, let's go back to our lawnmower problem. Now, we remind ourselves of the forces that act on the lawnmower. There is this applied force on an angle theta. There is going to be weight, mg. There's going to be the normal force from the surface, and there's going to be friction, which resists sliding. Okay? Now, this applied force is partly down, that's F sine theta, and partly to the right, that's F cos theta. Let's call them, for the sake of this drawing, let's call them Fy and Fx. So this is not going to cooperate, I can just tell. Come on now. There we go. So this one is Fy. Let's try that one more time. There we go. Fy for this component, and then this horizontal component is Fx. And did that cooperate? Not especially well. All right, so this is Fx. I don't know where the F is gone, but it's disappeared. One last time, Fx. So we see that there are some forces that are perpendicular to the direction of motion. You know, clearly this thing's going to move in the horizontal direction. So we've got the y component of the applied force, we've got the weight, and we've got the normal force, which are all perpendicular to the direction that the object is moving. Well, they actually do no work because there's no motion in this direction, therefore no y displacement means y forces do no work. Friction, as we've seen, is opposite to motion and does negative work. So the only force that's actually doing positive work and making this thing go is the x component of the applied force. So, as we have written down here, that's kind of what we were saying as we were filling in that chart. We want to try and represent this in a formula then, and the way to do that is to say that work is done by the component of force that's parallel to motion, and we'll use these two little lines here to represent parallel. So we'll say work is F parallel times D. Now it turns out that there's another way to write that, because if we look at the force and displacement vectors and we consider the angle between them, okay, then there turns out to be a nice relationship. First of all, let's remind ourselves that in this case the work done was positive, right? Force is in the direction of motion. In this case, there is no displacement in this direction, so this force actually does no work. In this case, because they're opposite, it's negative work. In this case, we have to find the component that's in the direction of motion. That'll be this one right here. Well, that component from the triangle is going to be F cos theta times D. And what we notice is that this equation actually works in all the diagrams, because here the angle between those two vectors is 0 degrees, and the cos of 0 is positive. Here the angle between those two vectors is 90 degrees, and the cos of 90 is 0. Here the angle between these two vectors is 180 degrees, because they're opposite to each other. And the cos of 180 is negative, so that again corresponds with what we expect for the work. So this gives us a nice, succinct way of summarizing all of that information. So let's do a two-dimensional problem now. We'll have you pause the tape here, and for this lawnmower problem, first start by writing your force equations, then calculate correctly the force of friction, and then find the work done by the applied force and the work done by friction. We'll pause the recording here. Step was to complete the force diagram, so we added in normal force, weight, friction, and the two components of force, and then to write force equations. Well, in the y direction, as we did the lawnmower problem a few classes ago, there's no motion, no acceleration, balanced forces. So the upwards normal force has to equal the downwards weight and the downwards y component. So hopefully you work this out correctly. So this will be 15 times 9.8 plus the applied force, which is 80 newtons, 80 sine of 32 degrees. So that gives you your normal force. Then to find your friction force, you have to multiply that by mu. Mu is given as 0.12. And then calculate the force of friction. Once you've done that, find the work done by the applied force and the work done by friction. Okay, so your normal force should work out to be 189.4 newtons, and your friction should be 22.7 newtons. So when you go to find the work done then by the applied force, remember that it's the force component parallel to motion. So the one that does work is actually the x component. It's actually F cos 32 times the distance, which is given as 6.75 meters. So that should work out, if you use the correct x component of force, to be 457.9 joules of work done. That's part A. So that's the amount of motion energy. And you're pushing on it, so food energy gets converted to motion energy. So this amount of motion energy came from the food energy that you ate yesterday. Next, the work done by friction. Because friction is opposite to motion, we remember that it should be negative. Our force of friction, which if we calculate using force analysis, we should get 22.7 newtons. We multiply that by the 6.75 meters of distance, and we get, for the work done by friction, 153.4 joules. So that completes our first lesson, and there will be a homework assignment on the Moodle site that's related to that. Let's continue on at this point and spend a bit of time on the second lesson, which has to do with the interpretation of graphs. Now, you will have done some of this in the lab, and you will, as you continue taking physics courses, see that this is a fairly common and important technique in physics. We will often make graphs of experimental data and then draw conclusions from those graphs. One really important experiment in physics is to measure the force that's required to extend a spring. And if you measure that, you find that with more extension, as you stretch the spring more force is required. Or another way to put that is, if you pull a little bit more, it stretches a little bit more in direct proportion. Okay? This is known as Hooke's law. And K, which is the coefficient of proportionality, is known as the spring constant of the spring. Let's imagine we had a spring with a 1.5 Newton per meter spring constant. Now that means for each meter of stretch, another 1.5 newtons is required. Or conversely, if we apply another 1.5 newtons, then it will stretch another meter further. Now, what this means is, if it's not stretched at all, then there's no force. To stretch it a meter, you would need 1.5 newtons of force. To stretch it 2 meters, you would just need 2 meters times this, you would need 3 newtons of force. To stretch it another meter, you'd need another 1.5 newtons, so 4.5 newtons of force would be required for that. Now, if we plot that graph, so 1 meter, 1.5, 0, 0, 2 meters, it's up here at 3, and then 3 meters, it's up at 4.5. What we notice is that those points lie on a nice straight line. So we can get out our ruler and draw a nice straight line there. And the wonderful thing about straight lines is you can find their slope. A slope is a rise over a run. So we see that we had 4.5 newtons of rise right here and 3 meters of run along the x-axis. Well, 4.5 over 3 is actually 1.5 newtons per every meter, and we identify that with the elastic constant of the spring. That's what was given. So this is how you actually find the elastic constant. You do this experiment and then you plot the graph. While we're on the subject of this graph, though, let's find the area. Well, the area, it's a triangular piece, and it's got a base of 3 meters and a height of 4.5 newtons. And we know that for triangles, the area is half base times height. So we've got a half times 3 meters times 4.5 newtons. So that's 13.5 over 2. That is a little bit more than 6. That is 6.75 units of area. But let's look at the dimensions, right? This would be in units of Newton meters. Well, a Newton meter is, of course, a joule. So we see that this area likely is related to the work that's done. So the work done, if you have a force-distance graph, can be identified as the area under that graph. That makes a lot of sense. If you're applying a constant force over a distance, if you've got a force-distance graph, then the area in this case is just the force times the distance, because the force is that side of the rectangle and the distance is this side of the rectangle. So that would be 3 newtons times 5 meters. There's 15 joules of work done according to this graph. 15 joules. Now, in the case of a triangle, like we had with spring on the previous page, here the work done is, well, we're going to have to find the area, right? And that's going to be a half times the base times the height. Well, the base is 2 meters, and that's pretty clearly the distance. The height is 10 newtons. And what we realize is that this 10 newtons has a physical representation, has a physical significance. It represents the average force. Rather, not the 10 newtons, but the 10 newtons over 2. Because if we start with 0 newtons and we end up with 10 newtons, then on average we were exerting 5 newtons, which is 10 over 2. So the area makes sense in this case because it really is telling us the average force, okay, times the distance. And so the product here, by the way, just ends up being 10 joules of work. Now, we can analyze other more complicated systems using the same idea. Sometimes, depending on the type of material, the force will stop increasing when actually go constant. So the work in that case would just be the area of the triangle plus the area of the rectangle that's left over at the end. And that's easy enough to solve. You can even find the area under curves and use that to compute the work done. So graphs are important tools in physics. You've seen in your lab that if you have a distance time graph, then the slope of that distance time graph, rise over run, is meters per second, and that tells you the velocity of the object. If you have a velocity time graph, then its slope, well, it would be a rise over run. So this graph, it would be 5 meters per second over 2 seconds, and it's a positive slope, so it would be 2.5 meters per second per second. Clearly, that is the acceleration. If you find the area, then that's going to be a half base times height. If you look at the dimensions that you get there, so that's a half times 5 meters per second times 2 seconds. Let me try writing it up here. Half times 5 meters per second times 2 seconds. Can we see it now? Yes, we can. Okay, so the 2's cancel out and you just end up with 5. But what's interesting is the units. The seconds cancel up and you end up with 5 meters. So what the area is telling us then is the displacement. So graphical analysis is a really powerful tool in physics. Next, the third lesson in this new unit is the relationship between work and energy. Now, we mentioned very briefly earlier on that work was an energy change. We're going to elaborate on that a little bit now.